Greetings, everyone. My name is Peter Dyke. Welcome to another edition of the Alliance's webinar program, where today we get to talk about PE Alliance calculators. Much of this data comes from PPI, but then our engineers have taken a look at that information and said, let's go deeper in certain areas, and that is what we're going to talk about today. Pretty excited about it. Alan Ambler, come on and say hello and tell us a little bit about who you are and what you do.
Hey there, Peter. Glad to be here today. I am a lead civil engineer for the Alliance for PE Pipe and put together today's presentation on all sorts of things that are calculators that we have. A calculator, as far as a resource is concerned, it is there for you and able to help you with your particular project that you're going through there. Got a project? We'd love to talk about all things HDPE. So definitely give us a shout and we'll talk to you about your particular project. We do very often talk about HDPE projects all throughout the industry and love to share that information and can put you right in connection with our champions and our experts, just like we're going to do here today on all the calculators. Isn't that right, Peter?
It is. So I like to talk about training. This is kind of our kick this year, Alan, as we talk about training and all the places where we can get it. So those 5 companies on the left, McElroy, Strongbridge, Integrity, George Fisher, they provide electrofusion training and butt fusion training for everybody. And then in the middle and on the right, we have our distributors, Alan. These are our distributors that also provide training. Almost all of them do, in addition to selling the products that we talk about here. So training is super important. One thing that distinguishes us from other materials is we need a higher level of training. We're proud of that because once you fuse it correctly, you end up with a product that's going to last hundreds of years. Next slide, Ian. Okay, Alan, you and your fellow engineers provide a bunch of free services. What are they?
Absolutely. So if you go to pepipe.org, you'll be able to see what our engineers package is that has a ton of great information on it, including specifications. We do project reviews and assistance. We'll schedule a seminar with you to be able to talk about your specific problem in your specific project as we go through. But that engineers package is easily downloadable and then it also has tons of specs. Insider's Guide to verbiage for PE pipe and all sorts of other great information, Peter.
So Alan spent a lot of time putting this deck together. This is the first time we've done it at this level. I think we've done calculators at Showcase before, haven't we, Alan?
Absolutely. Yes, sir.
But we have a lot of people to say thank you to, and they're listed here. And I'm sure that we've missed some, Alan, but we don't get to talk about this stuff if people haven't spent time on it before us. My good friends at Robar, and this is Jonathan Reinheimer, they make mechanical connections, and these are good for repair of HDPE as well as for transitions from HDPE to other materials. Most of them are custom, but we're going to be doing a webinar later in April where we just focus on HDPE specialty products, and Jonathan's going to come on and talk a little bit about Robar's products. So today, I'd like to bring on Richard and Stephen. Both of these guys are well known to our audience, certainly. Richard, tell us a little bit about Richard Kolasa and what you do for WL Plastics.
Good afternoon, everybody, or morning, wherever you are. My name is Richard Kolasa. I'm with WL Plastics. I'm the technical service manager there and do a lot of the engineering work between sales and engineering to make sure that municipalities or whoever the engineering firms understand the product properly and hopefully take down any barriers for understanding. So I'm really happy to be here today and look forward to the presentation.
Well, that's a great photograph of you, Richard. It looks a lot better on the photographs than you do in person. So I'm thankful for that. Stephen Boros, welcome to the Alliance's webinar program this week.
Hey, good afternoon, Peter. Thanks. No, glad to be here for another PE Alliance. Fantastic educational webinar. Always happy to participate in these things. And I learn a lot as we go through this as well. So looking forward to it this afternoon.
You know, Stephen, if you didn't get a chance, we did a webinar a couple weeks ago on data centers. And we got to learn a lot about PPRCT. I mean, I think you participated in that,
Yeah.
and polyethylene. And we got a bunch of projects that people wanted help with as a result. And I'm thankful for that. I mean, I'm so excited about those data center opportunities.
Oh yeah, that's a really hot area right now. I mean, can't get enough piping to go into those projects. So, yep, you're right.
So keep making the pipe, Stephen and Richard. And well, guys, we're going to bring you back in a minute. You're our primary experts today.
And without further ado, Peter, we're going to get started here on open cut calculations. It's a little dry, but all of those design engineers that are out there, next slide, I definitely can show what we're trying to look at from an actual calculation standpoint. So in direct burial, a ductile iron PVC and HDPE are all considered to be flexible pipes. So what we're looking at is that pipeline itself works with the soil that surrounds that pipe to be able to distribute the load. It's different from a rigid pipe. A rigid pipe, that hoop stress or hoop strength through that pipe is much stronger than the soil, and then they look to be able to distribute the loading in that manner itself. So ductile iron, PVC, and HDPE are all considered to be flexible pipe materials with regard to its interaction with the actual soil. So what we're taking a look at here that's unique to HDPE happens to be creep. And if you go through the animation there, we'll look at stress relaxation. What creep basically is essentially we're stressing that pipe or moving that pipe as we go through it. So it's very flexible in our HDPE and allows us to have great working characteristics while we're working with it from a contractor standpoint. And then we'll have stress relaxation. So that pipe, once we stop putting pressure on that pipe to be able to put it into a new shape or a new arrangement there, then that pipe will relax and it'll become a happy pipe. So that's stress relaxation is part of it. That is unique to HDPE. So this graphic here, yes, Richard.
I just want to make clear on that last slide. Everything looks like it's underground and that movement occurs. So when we talk about this movement or this viscoelastic behavior, it's really unrestrained. So it's like the pipe is just floating in air. So when we look at our calculations, we don't look at it as it's compacted in the soils. We want to have that understanding that this will occur when there is no resistant forces holding that pipe in place.
Absolutely. So that's during the actual construction period as to which we're installing the pipe, and then we put the soil that surrounds that pipe to have a soil stiffness factor through it as well. If we don't have the soil that surrounds this pipe, just like what we'd see here, then we're going to have that creep occur over time period. So we're going to put some stress on this pipe during the actual installation, a loading condition. Without that soil that surrounds it, then we'll have that creep occur. And you'll see as we come through this, by the time that we put the soil surrounding this pipe itself, that pipe stiffness factor interacts with the soil stiffness factor, and then we'll get support and distribution of that load through this soil column, and then we won't have the creep that's associated with pipe that did not have the soil with it as well. So you'll see through this as we have that relaxation period and we have that soil that surrounds it. Keep going. You won't have that deformation. So here's the technology or terminology of the pipe embedment materials there. We have embedment, trench wall, bedding, foundation, and backfill. All of these things work together to be able to distribute the load vertically from either a live load or a soil load as we go through it. And then we will look at how that trench reacts with the pipe to be able to distribute those loads. So what we're looking at in this video here happens to be a perfectly good trench through the process of installing the pipe. So we do have that foundation, which is the undisturbed soil at the bottom of this. Then we have a bedding, which is a soft spot for that pipe to be able to lay down against. Then we will embed the material and then also backfill on top of that to be able to put this through. One of the cool things about HDPE is the fact that we don't necessarily need to put people in the trench in this scenario, and it can be very productive install. Yes, Peter.
You know, Alan, we've talked about this video several times. I love this video, not only because people think that it's an unsafe trench, but that gets us talking about one of the key distinguishing features of polyethylene versus, let's just take PVC, is we can use much more narrow trench widths than they can because of the need to not put a man in the trench with HDPE, right?
Absolutely, Peter. Absolutely. Way more productive in that.
And that said, but we have a flange or an MJ connection here closest to us at the bottom at 6 o'clock. What do we do in that situation?
In that situation, you'd have that person get into the trench and make that final connection as we go through it. We can't have an entirely HDPE system for municipal water and wastewater in some instances because we do not make valves or other things fully out of HDPE in larger diameters. So there will have to be some type of connection as we go through. And in that scenario, you'll have a person in the trench, in the excavation, in order to be able to perform that final connection as we go through. All of these things, this is a perfectly good trench as we see it. AWWA's M55 gives us some design guidance. This is from a previous edition that shows us a design window. 98% of your installs are going to be within this design window. So if you're DR7 to a DR21, minimum depth of cover with an H20 loading at 3 feet, minimum depth of cover without the H20 loading is 2 feet, and a maximum depth of cover at 25 feet. Most of your designs won't need calculations at all. So if you do have something outside of that design window, then you would go through the actual extent of calculating. And guess what? The Alliance has those calculators and also has the spreadsheets for you. Stephen.
Yeah, just go back to that last slide real quick. I just want to point out there that, a real key part of this, and I think you mentioned it earlier, is, all right, we don't want to get guys down in the ditch. All right, so what do we do about compaction around those narrow trench walls or in the haunches? Well, this is an interesting part here. If you look at the design window requirements, all you need is a soil modulus of at least 200 psi. I mean, that literally just means you have at least class 3 soil, 2 or 3 soil that you just drop in. If it drops in, you're going to get around 200 or to 1,000 psi without getting in there and doing extensive tamping and backfilling and compaction. So really, there's not a need to worry about that aspect of it. I think that's a real key part of this entire non-engineered calculation that I want people to understand. You don't always have to get down there and make sure you get that haunch 100% compacted all the way around it up to the spring line. As long as you get anything in there at all, you're going to get at least 200 psi soil modulus or effective soil modulus on that.
We didn't put this in this deck, but a remedial class for the younger folks on class 1 to class 5 soil classifications and how that impacts the pipeline, please.
Yeah, we have a slide on that later on we can point out as it comes up as well. But thanks, Alan. Appreciate you letting me jump in.
Oh, no problem. Keep going if you would like to.
No,
so
you're good.
Just to address Peter's topic there, class 5 soil happens to be organics, peats, moss, any type of thing that we do not want around any pipe, no matter what the pipe design is. And then we'll get up to a class 1, which happens to be the stiffest backfill that we could put around there and maintain. So we're looking at how that pipe stiffness interaction has an interaction with the soil modulus. Both of those things work together to be able to distribute the loads, and we can easily take a look at this as we go through it. The equations that we're going to look at here happen to be deflection, wall buckling, unconstrained pipe, so that's in a vacuum scenario, and then also wall compressive stress. So all of these come from the AWWA M55 manual, and we do have a spreadsheet to be able to help you estimate these and calculate these deflections as we go through it, all of these equations. So these spreadsheets are available to you for whatever your project is. Just send us a note. We'd be more than happy to be able to send these out to you and continue to help you with your project development as we go through. Advance. So that pipe stiffness factor, when we get into a heavier, thicker wall pipe, that DR7 0.3 is 1600 psi. So that's just the pipe itself. And then when we look at a DR32.5, that's 12.5 psi. So that is an engineered backfill that we're going to put back with the DR32.5, in which case the soil that surrounds that DR32.5 is going to take over a lot more of the loading condition than what we'd see for a DR7.3. So both of those things work together in order to be able to distribute the loads, which you'll see in this equation as we go through it as well. So it is significantly higher. Obviously, it's 1600 psi, then 12.5 psi as we go through. As we look at the soil reaction, this is the table that Stephen had talked about. And then we look at the effects of actually compacting the soil. And what you'll see non-compacted on the left side and then compacted on the right side, even a class 3 soil can give us that 200 psi that Stephen had discussed about within the design window itself. So by the time that we put any amount of compaction through this pipe and soil stiffness itself, we're going to significantly distribute those loads as we go through that. So
before we
yep.
move on from this, it's just an anonymous attendee just asked this question. So basically, is what you're saying that HDPE is more forgiving than other materials when it comes to human error by contractors in meeting compaction requirements, or are you saying something different?
I'm not necessarily saying that it's more forgiving. The actual working with the contractor and using the pipe is a forgiving process because it's so much more flexible than other pipe materials. What I'm directly saying is all of that pipe stiffness factor plus the soil stiffness factor works together to be able to distribute the load, and it's not as big of a deal as one could otherwise make from a plastic material.
One of the things that people like to say, like particularly ductile iron, I mean, they're so proud of how strong they are, Alan or Stephen. What does that mean? And is that benefit really a benefit if people compact the soil properly?
I mean, that's a good question. So yes, the question is a more forgiving, and that's I guess it's a kind of your viewpoint type answer for that. In that, I think we covered this earlier. So anytime you have soil movement or you get some compaction or you get, deflection, something like that, it's going to generate a stress. And anytime you have a stress generated in a wall of the pipe, things can happen, and you have to design for that. The nice thing about polyethylene, I think this is where you're getting from for the more forgiving, is that it does stress relax. So once you get it into that constant strain and it stops moving, all right, you strained it, something happened, something moved, it deflected, and then it stopped. That stress in the wall of the pipe's going to reduce over time. And that's really key because now you have no more driving force to add additional stresses, or any driving force for any other type of failure mechanism is going to go away over time. And so that's where I think the term for more forgiving probably comes into play here.
All right. Good explanation. Thank you very much.
So what we'll also look at happens to be a live load. So we talked a little bit about stress relaxation. We talked about external conditions. One of the things that I'd like to really point out here is for pressurized pipe, the internal pressure trying to get out can often be exponentially bigger than what is exterior loading on the pipe. And so I'll point to 8 foot of depth with a live load of the box truck. So this is a Penske fully loaded with the Alliance for PE Pipes gear as we come to a roadshow for you. The external loading conditions at 8 foot depth is going to be less than 1 psi. So a DR11 that happens to be rated for 200 psi, that's going to be exponentially higher than what we'd see its external loading condition in a 8 foot depth. So that's exactly why we talk about these, and we show you what these actual calculators will do. This is a 4-foot depth of cover, 6-inch DR17, and then also a 45-foot depth of cover for a 6-inch DR11. We're going to show you exponentially the earth load pressure on the 45-foot depth of cover is going to be our highest one at 45 psi, but a DR11, of course, is a 200 psi rated pipe, and a DR17 at 4-foot depth of cover, the highest load there is going to be that 4.2 psi of the box truck running over top of it in a flexible asphalt. So it's still not substantial with regard to a live loading condition. And then our calculators are here to be able to show you that. Richard?
Yeah, and the other important aspect here too is the modulus value for the polyethylene, because like we're talking about the data centers and all that stuff, some of these cooling systems are running at higher temperatures, so you need to take that into consideration, especially if you have the H20 loadings, because as you know, polyethylene, as you go up in temperature, will have a softening effect at higher temperatures, but is workable up to 140 degrees Fahrenheit. So just always consider that temperature and that modulus of the material as well.
Okay, thank you very
One
much,
of the
Richard.
things- One of the things
Go
I'd
ahead.
like to add, Alan, for the benefit of some of the newer people, I looked at the list today. You know, we had several hundred people on this call, Alan, and not everybody understands the difference between, if we say it's a 200 psi pipe, that it's a 200 plus a 200 surge psi pipe, whereas other materials, they go down, they derate once you add flow. Could you just give us a quick 30 seconds on that, Alan, as a refresher, please?
Sure. So HDPE itself allows us for 1.5 times that pressure class to be able to be what's called recurring surge. So that's 55 cycles a day. And occasional surge is 2 times the actual pressure class for 5 or 6 cycles per day for that occasional surge. So while we have a 200 psi pipe at DR11, we can actually resist surge pressures up to 400 psi with that pipe. Those pipes, PVC, ductile, they are differently designed with regard to AWWA and how we look at pressure class itself. So you'll have to look for the guidance that AWWA would give you for those information. So here's wall buckling. This is just another part of the calculator as we go through, and we take that specific scenario that we looked at to be able to calculate those. So a vacuum pressure, what we're looking at happens to be if we have full collapse within the pipe, and we'll see a DR11 can withstand that 118 psi versus a DR17 at the 29 psi that we're looking at. So with a thinner wall pipe, we will need to look at vacuum pressure if we expect to have some type of a break within that pipe. So vacuum pressures happens to be when the pump turns on, or if there's a break in a force main on a major hill or something like that. We'll be looking at that. Yeah. Yes, Peter or Stephen?
Yeah, Alan, just on that vacuum. So that's a really good point. Especially looking at force main design and things like that, which could go under vacuum if your vacuum relief valves fail or something like that. Even with a DR17, your allowable external pressure on that could be as much as almost full vacuum and not collapse. So of course it depends on your soil envelope, things like that. So it's not like you're going to have to worry about this type of full vacuum effect if your vacuum relief valves do fail in a force main. It's not going to damage the polyethylene unless you have much thinner walls, DR21, DR26, things like that, which are normally for gravity.
Absolutely, Stephen. Thank you very much. So we'll look at wall compressive strength as well through the different depths of cover as we go through, and then calculate this as we continue to go through in our calculators. Keep going. And then now here with thermal expansion or contraction calculations as we look through. So one of the things that I'd like to point out again before closing and moving on from open cut is 98% of your installs are going to be within that design window, and you do not really need to calculate a whole lot unless you have an extenuating circumstance. So Richard, you want to come on and guide us through HDPE temperature operating range as we're looking at this?
Yes, I would. Thank you. The because we have this viscoelastic behavior of polyethylene, we are very ductile to very, very low temperatures. Not that you would ever operate in a glass transition area of a minus 130, which is really unrealistic, but it's important to understand that you are ductile with high density polyethylene with the zeros and below zero type values. And that's really, really important. However, it does become contracted. So the amorphous areas do become tightened within the polymer itself. So this way, you still have that ductility, which is really, really important. But if you're trying to bend pipe around corners without fittings or transitions, and you're in that allowable zone of the allowable bend radius, you have that ability. But the forces required might be a little bit greater because it is a little bit more dense. Whereas amorphous materials, such as a PVC, they're brittle right at 221 degrees. So they're a brittle product. So having any bending or movements or moments on those pipes can add really intensified stresses on those products. So you do have that luxury, but know that it does change as your temperatures go down and up. So it becomes more flexible when you go higher and less flexible when you come down. And this is exactly what we have to understand, again, for the newer people on board today. Everything in polyethylene is evaluated at 73 degrees or ambient temperature. So that's our standard. That's our normal area. But you, in pressure operation, as you go up in temperature, you're going to lose some of that capability. You don't negatively impact the performance of the pipe. It just the polymer, it just becomes softer. So that aspect you have to understand. So we have these calculation design coefficients that we can put into the formulas for determining what your pressure is. For example, if you had a operating system at 65 degrees Fahrenheit or 65 psi at 120 degrees Fahrenheit, you would see a reduction in that DR17 or DR11, but it would still be able to maintain that for the lifetime of the product. So know that you can calculate that, and that sometimes applies to the testing ability when you do your pressure testing, because let's say the pipe is hot or you're testing above ground where you're in a hot situation where maybe it sat all day in the sun and it raised the temperature. You can still test at that 1.5 or 1.25 or whatever pressure test your specification requires. So you just have to calculate what that maximum pressure is. Yeah, Peter.
So Richard, last week when we did this data center, we had close to 600 people on the call, and we were talking about the three different pipe types. We were talking about polyethylene that's good to 140, PERT that's good to 180, and PPRCT that's good to mid 200s. And, it's not often that we get to talk about the other pipe types, but that limit with each pipe type really becomes evident in that type of application.
Oh, absolutely. And that's really vital because also not only it's the location of the polyethylene versus the other pipe types too, because PERTs and PPRTs are typically used inside. So you can transition from a polymer to a polymer. So it can absolutely reduce your stresses on those type of situations if you had those thermodynamic differences, right? Again, thermal expansion and contraction, one of the biggest areas that we're working on. We haven't really studied in the industry, all the effects of the soil types that add load onto this pipe and what those frictional resistances are on the pipe to maybe increase or reduce or eliminate stresses as they occur. But in this particular calculation, this is a unrestrained calculation that gives you an idea of what the worst case scenario would be for 100 feet of pipe and a 40-degree difference in temperature with the expansion and contraction value that we have. You're looking at in that 100 feet of 10-inch DR11 of 3.48 inches of expansion or contraction, depending on which direction you went. As you went cold, it'll be negative. As you went hot, it'll be positive. So, but that's not really a real concern. We just need to understand it because there's some stresses if you had a system that is above ground and you had some stresses that are applied with that expansion or contraction. We need to be able to manage those manage those expansion and contraction. So this is an example of using the modulus of high density of instantaneous 150,000 psi and carbon steel at 30 million. You can see that, the expansion for the carbon steel is, very, very small, and yet the high density is very, very large comparatively speaking. However, the stresses associated with that reaction is quite a bit lower than the steel. It's easier to manage 700 pounds than it is to manage 8,400 pounds.
So, I like to say, and Alan has counseled me on this for years, Richard, that that the thermal effects that we see are rare underground because of the soil friction that is observed. But right now in Washington, D.C., they've got a bunch of polyethylene trying to help them solve that 300 million wastewater dump of raw sewage into the Potomac River. They're not really worried about the thermal effects because it's a short run of polyethylene. They've got 7 100-foot runs. What do you see in the field? Does the thermal effects really affect the operation of these pipelines?
We're saying no. From experiences and what we see in the ground, if your total system is polyethylene, which all the joints and fusions and everything are self-restrained, we don't see that movement at all. And there was a specific example where we had in I think it was Minnesota, where they were calculating a 24-inch line that had open vaults with valves in these open vaults. And they were concerned that because of the length between the vaults was quite significant, they calculated the thermal expansion and contraction of this line of being fairly significant. And they're worried about the polyethylene pulling out of the valves in those areas. But when we look back at it, we looked at the soil modulus and how they were compacted. They wanted to put these great big restraint blocks, but we found that through the calculations that after about 2 or 3 feet, those stresses were completely relieved. So those valves weren't moving in those open areas.
Thank you.
And just one last comment, the inventor of the MJ adapter, which is Harvey Svetlik, I've talked to him on several occasions about, have you had any failures from pullouts of thermal expansion and contraction or Poisson's laws? And he said 0. His answer was 0. So there's obviously a significant soil contribution for restraint.
So, Richard, this I added new for us. Whenever I look at a above ground project and start to go through the design analysis, I look at temperature fluctuation through weather.com or some other type of app like that. And I'm looking to be able to see what actually an above ground pipe may very well experience, which we see this. Our literature that gives us the information and the equations to be able to perform the calculation tells us that half of those theoretical calculations is typically what is observed as far as a temperature fluctuation is concerned. So there's things like friction force that Richard had talked about through soil, either a full circumference if it's buried, or if it's not buried, then we're seeing a soil friction. If above ground, it's moving across that soil interface as well. But we are looking at those temperature fluctuations for actual field conditions to be able to try to go through and predict what kind of changes in thermal expansion or contraction we might see. Next slide.
Just one more comment on that.
Mm-hmm.
So it's really important to understand that this is not an instantaneous response. So you look at those graphs over time, it's going to take a long time for the pipe to change that temperature. So it doesn't happen instantaneous. So if you had 70 to 30 or whatever that number was over time, or that it's not going to happen instantaneously. And don't forget, as we talked about earlier, we have that viscoelastic behavioral loss who release that stress to avoid any kind of further strain on that pipe as well.
Absolutely, Richard. So those equations, what we're provided is an immediate temperature change. So they consider it to be instantaneous. So that's why we'll see that the actual movement that we have is less than that. So I'll also look at the project specifics itself to see if there's got some type of sun associated with an above ground. What you'll see here is a small amount of UV. and where this above ground pipe for temporary bypass was going to go. So I'll make assumptions about that particular project and the behavior of the pipe based on UV exposure through it as well. So as responsible design engineers, those are things that we take a look at when we are making these temperature assumptions. Again, that is probably one of the most challenging items to be able to take a look at as a design engineer, is that what exactly are our field conditions going to be with regard to temperature change. Now, the behavior of the pipe we can control. So we can either do so through what you'll see in the top graphic here, where we know we're going to have some movement, so we allow that pipe to be able to move, or you can judiciously restrain it, like you'll see in the middle here, where we'll look at stress that develops within that pipeline itself. So each one of those restraint locations, then we'll look at the stress, or a conventional expansion loop if necessary through this process. So sometimes it's pretty simple, as what you'll see in the bottom picture on the previous slide was a jersey barrier that's just there to help straighten that pipe out as we go through. So we'll look at a calculator for HDPE app. So that is also a PPI calculator that allow you to go through and take a look at your specific application and plug in everything that you need right there online for you. So it'll look at all of those conditions. In the Alliance's spreadsheets, what we'll do is show you all the calculations as well as pull where they actually come from. So here's our calculators for the Alliance. We'll take a look at DR rating. We'll take a look at support spacing requirements, and then also show you where we pull this information from. We'll translate from a expansion or contraction directly into a stress based on the DR and the size of the pipe as we go through there, and all of this is available for you. So our above ground, we're looking at that unrestrained length change, maximum pull forces and anchor forces, suspended pipe support spans, and all those things in there as well. I'm very happy that Richard had pointed out that the soil column surrounding the pipe for buried applications oftentimes absorbs quite a bit of that change as well. Yes, Peter?
In effect, under below ground, it says thrust block sizing. Should that be anchor block sizing?
Thank you very much. Yes, it should be anchor block sizing, as thrust blocks are specific to changes in pressure. Anchor blocks are going to be a terminal connection with another different type of pipe material or changes with the actual system itself. Thank you very much for that, Peter. Appreciate it.
Yeah, not to be that guy, but you've preached that to me over the years, and one of the key distinguishing factors of polyethylene versus legacy materials is we are fully self-restrained, so the need for a thrust block doesn't exist. However, the need for an anchor block does exist. Am I correct?
That is correct. When we're changing material types or connecting to other systems, and we're looking at those scenarios, we will always look at our design requirements for anchor blocking. Yes, Richard?
Yeah, that's just been recently changed just because the MAB, the Municipal Advisory Board of the Plastics Pipe Institute, redid all the calculations for those anchor and thrust blocks. So they want to call them anchor blocks now because then they have the friction resistances and everything to reduce the size of them. So they're not as big as they used to be, but there was a change there that just recently happened. So that's part of it as well.
Awesome. So in above ground scenarios, sometimes it's just easy. What you'll see here, you can dump some earth right on top of that pipe to be able to hold it in place. We can use helical anchors, concrete profile blocks, any type of connection. We need to make sure that there's a rubber padding in between a metallic portion and also the HDPE to make sure we're protecting the HDPE as we go through there. But the above ground uses sometimes can be pretty straightforward as far as how we restrain that pipe. So we'll look through. Yes, Richard?
Yeah, and it's also important to understand that when you put those brackets in there and they're tightened down and they're holding that pipe in place, that's a restraint. So now you divide your distance from those points within those anchor locations.
Absolutely. So I'm going to use a term that Peter said earlier, which is forgiving. And if we can look at a 50-degree temperature change through the deflection and strain, while we may very well move quite a bit because of that massive temperature change through HDPE, our strain within the pipeline itself is not going to be as high as other pipe material. And this is very specifically due to the fact that the force required to stop the movement of the pipe isn't as high as other types of materials. That has to do with the modulus of elasticity, specific to HDPE. And as you can see here, 100-foot restraint, even though we may very well move 54 inches, in between those restraints, the strain developed at the restraint itself is less than 0.56 or 0.56%. So as we look through the design of these systems on bridge structures or otherwise, pressurized pipelines, we would look for each of the stress at each of the connections. For non-pressurized pipelines, we're going to make sure that pipe doesn't sump or doesn't have a low spot as we're moving that along. That's going to be our design guidance as we keep through. And then also here you'll see that rubber connection while we're holding that pipe into place on wherever it is that we're putting that pipe itself. So we want to make sure that it's robust, the connection that we have, and then also is not being detrimental to the HDPE through a direct connection. So here's some support spacing design, the steps that we're looking for. I talked about a sump. We're talking about deflection as well, which we'll look at the deflection in between each of the connections as we go through. The beam deflection analysis is the equation that we run through to be able to take a look at how this deflection actually occurs, advance. So we'll take a look at the max allowable bending stress through this process. Yes, Richard?
Yeah, just a quick note on that last picture that you had. If you notice, they had rollers, not clamps. So this pipe was actually allowed to move. So they actually designed it to allow it to slide back and forth on there to alleviate any kind of stresses.
That's an easy way to be able to get through that. Absolutely. Thank you very much for pointing that out there. So here's just the equation that we have. We do translate this into the calculator for you as well. So while we are looking at span-to-span length and stresses that determine within it, we are also looking at the fluid density and weight as it's conveyed through this pipe. So we have the pipe, plus we have the pipe, the weight of the fluid within the pipe, and then we will translate that directly to that deflection calculation as we're seeing here. So a 10-inch pipe, when we're looking at 100 psi bending stress with 13.45 feet in between spacings there, we're looking at 0.00002896 inches of deflection. So we are not deflecting a whole lot within this pipe, and it's simply not moving for us in that process. So now we're going to get to horizontal directional drill. Here we'll talk to you about the design metrics that we're going to be looking for HDD as well. So these are our general items for complex or challenging HDD installs. We recommend that you go to a professional engineer that is very familiar with HDD as well. So we're looking at basically an intelligent tool coming through. And we can track where that tool is, as you're seeing here. And as we go through to the obstruction, as we are clearing some type of an obstruction, either a river or a road or something of that nature, we will track exactly where that intelligent tool is. And then once we have the original bore path come through and it's in the proper alignment, then we can expand that hole through reamers and other things as well, advance, and we'll move this material as we enlarge that bore path, and then we'll start to pull that production pipeline back into place as we're moving this into final HDD. So here's some reference documents. Our spreadsheets that we have developed with the Alliance are based on ASTM F1962 to give you general information as to what we would calculate and develop from a planning tool such as BoardAid all the way to actual calculations within our spreadsheets themselves. So with HDD design, what we're looking at is the geometry, available space, existing utilities and restrictions. We're trying to find a path that is free and clear of any type of obstruction that would preclude us from being able to put in a successful horizontal directional drill. We want to look at material properties of the pipe and then also soil properties from what we're going to be drilling through. We look at the entrance and exit angles, bend radius, minimum length for clearance depth. With regard to HDPE, that bend radius, or the allowable bending radius of the HDPE material, is more forgiving than what we'd see in a drill string itself. So that entrance and exit angles are going to be a primary limiter from the equipment that's installing the pipe, and then also the drill string as we go through that. So we look at rig capability, pipe size and material, installation geometry. We'll want to be able to make sure that whatever bore path that we're designing as a respectful engineer is able to be constructed by the equipment that's out there for this, to be able to put that into the ground and then also show us the forces that are necessary or develop as we're installing this pipeline. So what we're looking at from a safe pull force standpoint happens to be HDPE is buoyant, so sometimes it'll undergo what's called the capstan effect, which it'll float within this bore path as we see there, and then develop friction forces along those bends. As we achieve those bends through there, we can add ballast to this pipe as it's being pulled into place, which can either be water or other dense fluid within the pipeline, in order to be able to drop that pipe down and reduce that friction force. And we'll take a look at those items as well while we design them. And the easiest parameter to get to is that allowable safe pull force. This is a table that the industry simply presented and shows us the DR rating and the allowable tensile yield strength of that pipe as assumptions we go through. And then you can apply different factors of safety or environmental factors as we look through here. Yes, Peter.
We just got a question that calls to mind something pretty interesting. It's tangential here, Alan. Sorry to take us down this little rabbit hole. The question was, how big a drill have we done? What's the biggest drill? The biggest drill I know of is 54-inch. We did a 54-inch DR-17 in Miami Beach 8 years ago. That one has been celebrated in the industry. It was a huge job. Last year in 2025, we did 2 huge drills. One of them was down in Fort Lauderdale. We did a 54-inch DR-11, and that was pushing the limits. And then Garney did one under the James River, Alan. It was a 48-inch DR-11, I believe. And it included some 54-inch 11 that was open cut once it crossed the river. And that one has been celebrated. It's been in a lot of the press. So those are the big ones that we're doing as far as I know.
Those are great projects, Peter. Thank you very much for providing the information for us here. You engineers out there continuing to push the boundaries, and the contractors are more than happy to take some risk with you to be able to make sure that we have what we need to be able to push that. Stephen, you want to come on and talk to us about PPI BoreAid and a preliminary design calculator?
Yeah, be happy to. Thanks, Alan. So yeah, this is an online calculator put out by the Plastics Pipe Institute, www.ppiboreaid.com. Remember to use PPI BoreAid, because I think Vermeer, and I'm not sure if they still use it, did license the BoreAid name afterwards and have their own design calculator. But this is the PPI BoreAid version, free to use online. And this will cover, I don't know, maybe 80+% of all directional drill design that you're going to need to worry about. There's a few geotechnical things you can't get to, but mostly you can get it. So you start by putting in your pipe type, P4710, then you pick your nominal diameter. It's a great tool to look at different scenarios as well. So say, all right, I'm going to use this diameter pipe and I think I need DR11. So let's pick 36-inch DR11, and then we'll go to step 2, which is the bore path. And it's going to give you some pre-selected numbers here, and it gives you your potential bore path here. And you look at, your L1, L2, L3, and L4. All those add up together for your total directional drill bore path and how much pipe you're going to need to achieve that path. So you got to remember, it's not a straight run. You got the down angle. It's going to let you pick angles that make sense as well. So for a pipe entry angle, it's not going to let you pick 45 degrees or something like that, which you can't do with a drill string. So you don't have to be an expert on this, and it'll just help you get through there. So once you put in all your soil depths, your water table ratings, and things like that, it'll give you your total length that you need. And then you go to your calculation. So there's two main things you need to look at that will be critical for a successful bore. So first of all, it's going to be your allowable pullback force. So you can see over here under installation, your pullback force and allowable pullback force. This is the calculated that you're likely to see, and here's what the pipes can maximally do. And the nice part about this is, remember in the example, we picked 36-inch DR11. So it gives you 3 different scenarios indicated by these orange blocks here on the left. So worst case scenario, no rollers, no ballast. You're just going to pull this long string of pipe into place. So you're going to have some significant pull forces on the pipe itself. And it's going to tell you whether DR11 will work, or whether DR13.5 will work, a thinner wall, or if you maybe need to go to a heavier wall, the DR9. So it gives you all those scenarios to see what's going to work from a pullback force, but just as important, a collapse force. So you got to remember, you got a lot of collapse forces working on that, pipe buoyant forces, capstan forces, that all have to be calculated, and PPI Bore 8 does that for you. Now, if you want to say, all right, I don't know if I want to use DR13.5, what if I go down here to the third scenario where I'm going to use rollers? So I'm going to minimize that pullback force of that long pipe string. I'm going to put ballast in the pipe. I'm going to fill it with water to give it more rigidity, more stiffness against buckling. Could I use a DR13.5 in that instance? And that'll show you that, yep, you absolutely can. So if that's critical for you, there are ways to get through that to get a passing, if you will, or a successful bore design. It's a great tool to go back and forth and look at these. So if you look at the schematic of what a pipe string is, I think Alan talked about this a little bit before. On the left-hand side is where your drill rig's going to be. You're going to do your initial bore path. It's going to come through with your tool. And remember, even today with polyethylene, you could do compound curves on this. Now, you can't do wild curves, but if you needed to curve around an obstruction or possibly a mild S-shaped curve, you can do that underground and then come back at your exit point at A, then come back with your back reamer and then pull the polyethylene pipe back in, take into account this different bore path that you may have. So it's a great tool, and that's what, again, the flexibility of polyethylene really comes into play here. So again, you go back into the design progression, determine your OD and DR. PPI Bore 8 can help with that. Identify the minimum depth that you need in clearance under the obstructions to know, all right, how much depth am I going to have underneath the soil that I have to work with? You need good geotechnical drill samples to know what you're working with down there. If you have large cobbles, what types of soils you're dealing with. That's where a good geotechnical engineer comes into play on this and be well worth it. Determine the suitable entrance and exit angles. They're going to be nothing extreme. Remember, those are normally going to be limited by the flexibility of the drill string itself, not by the polyethylene. The polyethylene is going to be much more flexible than that drill string will allow. So normally your maximum entrance and exit angles are going to be limited by your drill string. The radius that you can have once you get down to depth, and then you can come to a vertical or a horizontal, and then your exit curves. All right, what is the total weight of the pipe, with and without ballast, frictional forces? What bore lengths am I going to need? All the way from the very beginning, exit down, all the way traverse, exit back out, and then come out at the top of the ground. So you're going to need all of those things, and PPI Bore 8 will give you a lot of that to calculate with. And it goes right along with ASTM standard, 1962, I believe it is.
Yeah, sorry, it's just a very valid point. Like, I've seen a lot of scenarios where, there's limited space for the drill. and the drill has tried to force some pretty tough angles in there. And then you have to think, well, whether it's even possible. If they do manage to do it, it could add extra stresses on the pipe. So the calculator will tell you if it's limited. So then if you run into that situation, just try a longer length or try a different depth to find out what your possibilities are to make that drill successful.
That's a good point. So yeah, sometimes even having a longer length will make a more successful drill, or a deeper bore will have a more successful drill than trying to keep it shallow. Excellent point. Now you get into one of my favorite calculators that's online is PPI PACE. So it's the www.ppipace.com. So what this is, a calculation environment to look at a true apples for apples comparison between polyethylene, ductile iron, and PVC in most municipal applications. So it's going to look at your different pipe sizes and different pressure classes. And this is a great tool for making sure you pick the right pressure class for each material. Remember, one of my biggest pet peeves on this for people to remember, all pressure class definitions are different for every material. So if you use pressure class defined by ductile iron, it's not the same as defined by PVC and not the same as defined by polyethylene. So you can't use pressure class for pressure class comparison and have a successful design. PPI PACE will help you with that. On the right-hand side, you can put in your actual operating or design parameters, your length of pipe you want to work with, recurring surge, occasional surge, your actual working pressure that you have on your system. How many anticipated surges are you going to have that day? Most force main design is going to be a minimum of 55, sometimes more. Your average underground temperature as well as your design life. You should never expect anything less than a 100-year design life today. There's also, if you click on the radial dots on each of those, it'll show you where that data comes from. Why do we pick 4 feet to 8 feet per second on flow velocities? Because that's how most systems are designed. And more importantly, how most systems are actually being operated based on surveys. So you might think it's only going to be operating at 4, but they could be as high as 8 at peak demand situations. On surges, like I said, if you look at the design manuals for polyethylene, PVC, ductile iron, specifications from a lot of major utilities, on a force main design, it's 55 surges per day. That's a lot to take into account. And PPI PACE helps you do that, because ultimately that's going to be how these materials fail, is by cyclic fatigue, if the material is susceptible to that. So once you put in all your parameters, then you get the actual design. All right, here's how my design comes out, looking at all the different materials: polyethylene, ductile iron, PVC, and you look at the different pressure class. Remember, this is a pressure class 125 polyethylene, pressure class 350 ductile iron, and a pressure class 235 PVC. How do these all work? Do they all have successful designs in this rigorous force main application? You can see here the maximum flow rate. Yeah, very comparable for all materials. Head loss, very comparable for all materials. Surge pressures, that's where it's going to be different. Polyethylene, you don't have to worry about surge pressures as much because it has a lower modulus. So that resulting energy change, that energy has to go somewhere. In a rigid material, it goes into the pipe wall and results in a high pressure spike. In polyethylene, because it's more flexible, it absorbs that energy, and the resultant pressure spike is much less, half or even a third as much. So it gives you the total surge as well as the working pressure rating to see if that all matches. But here's the real key, and you have to design for this because that's how it's going to fail. What is the fatigue requirement for the material? All materials have them. How many cycles to failure can they handle? Polyethylene can handle 15 million cycles at full range capacity, meaning full operating pressure class, and 1.5 times to 2 times above that for 15 million cycles and not fail. Make sure your other materials, you can do the same thing. And if they can't, maybe you need a thicker or a higher pressure class product. This is the same information graphically to show which ones pass and which ones fail. So this is not to show you that, ductile iron and PVC always fail. That's not what this is about. This is just under this type of situation. You pick different design parameters though, and then everything will work. You just have to pick the right ones and know and understand what you're designing for. And this is, I think, where we go into the other scenario. So let's say, for instance, you look at the top here. Now we're dealing with a pressure class 305 PVC. So essentially DR14 versus a DR18. What's the difference here? Well, in this scenario, polyethylene now has a higher flow capacity. And as you go down there, everything else works. The pressure surges work, but more importantly, the cyclic fatigue now works. Under this scenario, both materials can have a true 100-year design life. And I think that's very key that you're comparing apples for apples when you look at these design scenarios. Again, I think we mentioned this is another one I use frequently, HDPEapp.com. It's called S5 because that's what PPI had called it when they developed the program initially. But online, it's www.hdpeapp.com. And what this program will go through pretty much all the calculations within the PE pipe handbook. So you don't have to go through each one manually, and a lot of different scenarios. So you go along the top of the pipe, you put in your sizing classification, IPS or DIPS, the size of your nominal size of your pipe, and the DR pipe that you want to look at. Very initially, you just look at pipe properties. All right, what are my pipe properties down here? If you click on that More button, we can't do it here, it'll show you a whole list of pipe properties that are very helpful in over your overall design rating. It'll show you DR17 at 73 degrees, has a pressure rating of 125 PSI. That means it can operate at 120 PSI with flow up to probably 12 or 15 feet per second without having to derate that. If you go into some of the installation type of conditions, let's say I'm dealing with a pressure flow, just click on that button. Then it takes you to the next step and lets you pick different scenarios of how you want to design for pressure. So let's say, for instance, in this example, yeah,
Stephen, hang on a second.
Hey, Richard.
Yeah, hi. Sorry about that. I just want to go back because that oxidative calculator is also built in there under pressure flow. So if you know your water conditions for your system, and you can plug that into that as well, because chlorine resistance is always a big concern with degradation of any product, but with disinfectants in there. So just know that that's in there, so you can double check to make sure that you still can maintain that 100-year service life.
You know, that's an excellent point, Richard. I didn't touch on that point, but that is really good. And that'll let you look at that chlorine categorization that we have on polyethylene materials today. So if you didn't know, all C906 standards and C901 require a polyethylene material with a CC3 rating. So if you go through these oxidative resistance calculations with your exact water conditions, you will see that will give you a true 100-year design life against oxidative failure. So that's really key. That's going to be eliminated from a failure mechanism in your system.
So, Stephen, our competition likes to talk about polyethylene failing in the presence of chlorine. We did have an issue in some utilities 20 years ago. Could you give us the story of what happened, why it happened, and what the industry did to solve that issue?
Absolutely. Yeah, I was involved in all that, Peter. I've been doing this for a long time. And so back when there was a few instances where polyethylene over the time did end up failing, and it was determined that it failed because of oxidative degradation, which embrittles the material and causes small cracks to occur. So when you go back and investigate that, we found that it happened in two main reasons. First of all, you had a very aggressive water situation, and you had high annual operating temperatures, such as in the desert in Arizona, Las Vegas, things like that, more shallow burial situations. And you had materials that weren't designed specifically for resistance to chlorine disinfectants. So what we did is we took over a period of time, we took about a 5-year research study and developed models that would forecast that. And then we developed the test methods and new additive packages which could resist those types of failures. So now we have this additional testing requirement on polyethylene materials to specifically resist against those types of conditions, even in the worst case scenarios. The only ones that it doesn't apply to is going to be the use of chlorine dioxide. So if you do have a municipal system that's operating with chlorine dioxide, you can't apply this oxidative resistance calculator, but just contact your manufacturer to check on their recommendations. There are ways you can do that as well.
Thank you.
So let's go back to our pressure flow calculation real quick. Very simple scenario, 8-inch pipe. I have a mile of it. Here's my operating pressure, 80 to 100 PSI. I need 750 gallons per minute through there. All right, what kind of pressure drop in flow velocities am I likely to see? Well, first of all, you know right away that a DR11 can handle 200 psi maximum operating pressure. And that means a 300 psi means a 200 plus another 100 psi recurring surge capacity, and up to 400 psi on recurring occasional surge capacity. So when you go in and solve that, you can solve for it in different ways. Do I want frictional pressure loss? Do I want calculate what length of pipe I need to get a certain pressure loss, or my overall flow rate? For this situation, we want to look at what's my frictional loss. So over a mile of pipe, 8-inch DR11, you look over on the left-hand side as your results. So my frictional pressure loss over that mile is 37 psi. You're going, wow, that's really high. But you also look at, this is a mile, and you're operating at over 6 foot per second flow velocity. So you got a material that, or a fluid that's moving pretty quick through there. But the nice part of this is polyethylene can handle that. Even an instantaneous surge pressure would only be 90 psi. If you're operating at 100 and you have a 90 psi surge at that 6.3 feet per second flow velocity, water hammer effect, you're only going to have 190 or maybe 200 psi surge. That's well below even the pressure rating of the product, which in this case, it can go up to 400 psi. So even under those conditions, you're going to be just fine. So you can look at different situations like that to see what works. Is it going to be a valid design for what I need?
Okay.
You know, Stephen, that's one of the more interesting things about polyethylene. You know, I keep trying to identify ways our product is different from legacy materials. And in this, the way we accommodate surge is completely different, both in our ability to handle it, you know, above our pressure class. We don't reduce, but also the way we attenuate that surge from the material property standpoint.
Oh yeah, absolutely. And that's what gets back to my previous comment that pressure class is not defined the same for all materials. For polyethylene, pressure class means actual working pressure rating with a surge allowance above that. We don't design pipeline systems as static vessels. We design them as flowing vessels. We want stuff to flow through them. Otherwise, it's just a tank or a cylinder. And so when we have things flow through there, then different things can happen, and you have to account for that. Polyethylene has that unique ability to handle the surges above its pressure class rating, whereas most materials you have to subtract from the pressure class whatever surge you need, and that becomes your working pressure rating. So you got to remember to take that into account.
Yeah, Richard.
We run into this all the time, Stephen, and it's amazing. But if you truly understand this material and what its capabilities are, you're going to find that it's going to take care of a lot of the issues that we've had with legacy products in the future, especially if it's installed correctly and fused correctly. You can't overemphasize that. I know it's a kind of a bragging situation, but it's reality. We've got pilots in the ground for over 25 years that have operated without any failure or anything. So these calculators just help you get there to help you understand what these materials can do.